So this will be the final video for the section 8.2 content. We'll be talking about multiplying matrices again, and in this one we're going to try to answer the other two questions. So the first question was, how do we do it? And that's what we answered in the previous video. But now we're going to talk a little bit about the commutative property, how it applies to matrices, and also we're going to discuss when you can actually multiply two matrices together, because you can't multiply all of them. So first of all, a quick reminder of the commutative property. Essentially what the commutative property says is if I took something like 2 plus 3, I would get 5, and that's the same as 3 plus 2. Or if I did 4 times 7, that would be 28, and that's actually the same as 7 times 4. So from what we know about numbers, and these can be summarized, if I have a plus b, that's the same as b plus a times b. So with numbers, the commutative property holds. It doesn't matter what order we do these problems in. However, in the previous video, we showed that when I took d times e, I ended up with -2, -1, 2, and 0. But when I did e times d, I got something different. So you can always go back and look at the previous video or your notes, but notice that I actually got something different. So in this case, dE did not equal E times D. So for matrices, going back to, again, the previous videos, first of all, addition is commutative. We didn't show this, we didn't really have to, but if I took a plus b, that's the same as b plus a. But multiplication is not always commutative. In fact, most of the time it's not. Sometimes this will be true, but most of the time a times b does not equal b times a. So just kind of a word of caution there. If you're multiplying matrices, just know that a times b is not the same as b times a. Okay, so that's the first step. Now the next question I want to answer is, when can we multiply matrices? Because if you just threw a couple of random matrices out there, you might not be able to multiply them together. So here's what has to happen. If we say A, let's just let A be a, let's call it an n by m matrix. And let's let B be a p by q matrix. Then A times B exists only if m equals p. So notice if I'm kind of writing this down in terms of their orders, I'm taking an n by m matrix and I'm multiplying it by a p by q matrix. In order for this to work, m and p have to be the same number. And then the resultant matrix, A times B, will be a n by q matrix. So we actually know what the order of the final matrix will be. We take n by q. And so the orders play a huge role when we're multiplying matrices. Let's go back to an example, and I'm going to use some matrices in a previous video. So let's go ahead and use, I'll write them down again. A was 1, -3, 0, 2, 5, 1, 3, -4, -2, 0, 3, -5. B was the matrix 0, -1, 1, 4, 2, -3, 0, -5, and then 2, 3, -4, -1. I'll also include C here just so we have them all written down, because I do want to use C. Okay. Now remember, when we looked in the adding and subtracting videos, we said that A plus B, so just as a quick reminder, A plus B exists. We actually found out what that was, but we couldn't do A plus C. But now, notice that if I try to do A times B, let's call this example 1, I guess. We'll try to do A times B. If you try to do A times B, A is a 3 by 4, as is B. And because these are not equal, 4 and 3 are not equal, we can't actually do that. That's because if I wanted to try to take, let's say, row 1 from A, and I tried to do the thing where I mashed them together in the previous video. So I took 1, negative 3, 0, and 2. And I put that with B column 1, or any of the columns really. We're going to run out of stuff because B only has 3 rows to match up. And so because 2 doesn't have anything, it doesn't even have a 0. We can't just put a 0 there if we want. So because 2 doesn't have anything, we actually would just say this does not work. We run out of numbers to multiply by 2. So A times B does not exist. There's no solution there. Okay, so we're done with the first example. We didn't actually have to do anything there. Now, if we're looking back up at these problems, A was a 3 by 4, B was a 3 by 4, and I made C on purpose. I wanted it to have the same number of rows as the other ones had columns, so I actually could multiply these. So notice that A has 4 columns and C has 4 rows, so I'm going to now do A times C. A times C. Okay. So we're going to take A. Let me go ahead and just write that down here. A is 1, negative 3, 0, 2. And the next row is 5, 1, 3, negative 4. And then negative 2, 0, 3, negative 5. And I'm going to multiply this by C, which was 1, 0, negative 1, 2, 4, negative 3, and then 3, negative 2. Okay. So we're going to line up the rows and the columns, and we should end up with, because we have a 3 by 4 and a 4 by 2, we should end up with the answer should be a 3 by 2 matrix. So if we don't, we know we did something wrong. Okay, so let's do it. We're going to mash up the different rows. So as maybe an example, I'll do a couple of these. So we would have row 1 from A, and then column 1 from C. And so that would give me 1 times 1 plus negative 3 times negative 1 plus 0 times 4 plus 2 times 3. And so that gives me 1 plus 3 plus 0 plus 6, so I'd end up with 10. And you can do all the rest of them. I did this beforehand, so I'm going to pull up my answer real quick for that. So I end up with the answer. The first spot was that 10 we just found, then we get negative 10, 4, 1, negative 5, 1. Maybe I'll just, so this is the final answer, A times C. Maybe I'll just do one more. Let's do row 2, column 1. So I would take row 2, which is 5 times column 1, so times 1, plus 1 times -1 from, this is A and C I'm looking at, plus 3 times 4 plus -4 times 3. And so I should end up with 4 from that. Okay, so once again in this video we answered the commutative property, does that hold? And we also talked about when you can actually multiply a matrix. So that was the columns have to equal the rows being multiplied, and then we also know what the final order of the matrix will be. I want to point out, going back to the commutative property, we just did A times C, and that existed. But notice if I try to do C times A, this would be a 4 by 2 times a 3 by 4. So notice that 2 and that 3 are not actually equal. So this is a situation where AC exists, but C times A, this doesn't even exist. Not only is it a different matrix, but we can't even do it. So A times C works, but it's the commutative property doesn't hold in that C times A doesn't even exist. And that concludes section 8.2. So we've now seen matrix basics, we've added, subtracted them, we've defined them. And so you should be able to go through that homework now for